is unique in that there are no words taken out. Okay, and actually I'm not going to cover all of these slides. There's 44 slides in part 1, and we're not going to cover all of them. In part because, in fact, I'm going to skip that first slide and go right to definition of chemistry. One of the prereqs for getting in here is that you've already had chemistry, and so a lot of this actually in part 1 just kind of rehashes some of the basics. Okay, so chemistry is looking at, there's the periodic table of elements and how those elements combine to form compounds. Okay, you probably learned a long time ago that matter is anything, if it's matter, it must have mass and occupy space. Right. So we can kind of look at matter in a logic tree like this, where if it's broken into kind of halves, okay, where we have things that are pure and things that are mixtures, okay. So if it's pure, there are two options. It means it could be either just individual atoms of the same type of element, or those elements could be joined together. And of course like water, H2O, and 2 hydrogens, 1 oxygen, chemically joined together to make a compound. If it's a mixture, there's 2 options. It can be homogeneous, meaning it's the same throughout. Goodness. And heterogeneous, meaning it's chunky. I mean, it's not the same throughout. Boy, I cannot spell, but you get the idea. Okay. So part 1, this part that we're going to kind of quickly go over right now, this is kind of a summary of things that you need to kind of be able to know. The tree we just looked at of matter can be broken out into pure substances or substances and mixtures. Kind of know the difference between those. Elements versus compounds. Intensive versus extensive properties. I have a slide coming up to remind you what that looks like in case you haven't run into it before. Of course, a property, I bet you've run into before, all of these properties just means like a characteristic of matter, a way to describe that matter. Physical and chemical properties, physical and chemical changes, and that last one goes back to what you just saw on the logic tree. Mixtures, there's 2 types. There's ones that are really mixed, homogeneous mixture, and then there's the chunky mixtures, heterogeneous. Okay. So if something is a substance, that means, remember, it can either be an element or a compound, okay? But if it's a substance, you know it's got a set composition. Okay, and with a set composition, it's got distinctive properties that you can anticipate. Mixture is basically things are just physically tossed together. Okay, and it became a homogeneous or a heterogeneous mixture. So kind of from left to right, can you see where this blue liquid is homogeneous mixture, and the other one's chunky. It's a heterogeneous mixture. One of the things about mixtures is you can always separate them back out into the things that you physically combine together. An element means that the atoms are all the same. So if somebody says, I have a chunk of copper atoms here, then it's an element. The thing about, like in the case with the copper atoms, you cannot break the copper atoms down any further and for them to still be copper atoms. Okay, if you can go ahead and break them down further, but they won't be copper atoms anymore. Okay, so elements, as you probably already know, we use letter symbols to represent the elements, and sometimes they are 2 letters, like copper is capital C, lowercase u. And if there are 2 letters, the second letter is always lowercase. All right. So compound is where you have 2 or more types of atoms that are chemically bonded together. We'll be talking more about compounds, I think, clear in Unit 4 in this class. So compounds really lend themselves to using chemical formulas to describe the compound. Okay. Compounds can be broken down into their elements by ordinary chemical means. The opposite of ordinary is extraordinary, and opposite of ordinary chemical means would be some sort of nuclear chemistry. Okay, so back to the copper atom, you could do some sort of nuclear fission and break it down further. but a compound can be broken down into its elements. And an example of, I like this still image, an example of water, for instance, being broken down into hydrogen and oxygen can happen if you run an electrical current through it. So, in fact, this is like one of the ways that the hydrogen cell technology is maybe you can go ahead and get hydrogen from just water using electricity. All right, see how I'm just zooming through all of this, right? There are three physical phases of matter, okay? And they differ by, we'll be talking more about these intermolecular bonds, but the three physical phases of matter differ by, I think, two things. They differ by these bonds that are sticking the matter together, so kind of describe it this way. Down here, if I focus on a solid, okay, these have what we say a lot of bonds, intermolecular bonds versus chemical bonds. Okay, gases basically have no bonds, no intermolecular bonds. The other thing they differ by is with regard to how much motion they have. Gases have a lot of motion, and actually that motion translates to KE. What's KE stand for?
Kinetic energy.
Kinetic energy. Yep, that motion translates to a lot of kinetic energy. Solids, all matter has motion, so even solids have motion, so this is a minimum amount of motion. So minimum amount of energy, kinetic energy. Good. So aside from that, we can actually kind of look at those three phases of matter, and we can talk in terms of their size and shape. So for instance, if something is a solid, I bet you buy this, it's like rigid. Okay, if it's a solid, it means it's not going to change its size and it's not going to change its shape. So we say solids have a definite size and a definite shape. Skip forward to gases, okay? The cool thing about gases is that they have a lot of motion, they have no intermolecular bonds, okay? So in regards to their size, they basically take the size, anything you'll give them. Okay, gases. So their size is indefinite and their shape is indefinite. They, what we say, take on the shape of the container. Liquids take on the shape of the container, so their shape is indefinite, but liquids are kind of confined to a certain volume. Okay, so we say that their volume is so their volume or size is definite. All right. Okay. So properties. Properties are, I like to say, they're kind of like I'm thinking of game. So if you've ever played that, if you're on a long trip and you're like, somebody thinks of something and people ask them questions. Okay, so you ask them questions about properties. Okay, is it red? Okay, does it smell good? Okay, is it a living? Those are all properties or characteristics of what that person's thinking of. So matter can have different types of properties. A physical property of matter is something that can just be observed or measured physically without having to do any sort of chemistry. No chemical reaction has to occur. Okay? A chemical property can be measured, but this is the way I think of it. When you measure a chemical property, you better be done with your sample, okay? Because it's destructive. Any sort of measuring chemical properties would be a destructive test. The reason is you have a chemical reaction occur. Anytime you have a chemical reaction, a telltale sign of a chemical reaction is that new substances are formed. So let's say like you have a soil sample and you send it away to a lab and you need like a whole list of analysis. Okay, so the people running that soil sample will take note of the things that they can measure just physically, the non-destructive tests versus the chemical tests. chemical properties. So these actually are all physical properties. So if you look over here on the left, okay, all of that stuff is a characteristic of matter, but it doesn't require any chemical reaction to occur. They're important characteristics of matter that actually can help identify what the matter is. Okay, no molecules were harmed in the measuring of those, or atoms. So this is an example of the physical property of melting point temperature. Things melt or boil or freeze or condense at a particular temperature depending upon what the substance is. So boiling point temperature of water, about 100 Celsius. Okay, so kind of a quick and dirty test. You figure both of those test tubes are seeing 100 degrees Celsius. Okay, one of them has melted and one of them has not. That's because this naphthalene over here melts under 100 degrees Celsius, and this aspirin over here melts above 100 degrees Celsius. Just kind of a quick and dirty test. You could also smell them because naphthalene smells like mothballs. But again, sometimes students will kind of say, well, you apply heat, that seems like you're kind of messing with new substances might be formed because you apply heat. No. So picture taking this naphthalene back out of the hot water bath. Okay, it's going to freeze again, right? It's going to solidify, and those naphthalene molecules look the same before and after. Okay, so it's a physical property. So here's kind of a list. Look for new substances to be formed or not to be formed. When you say what something's color is, that's a physical property. When iron transforms into rust, iron is Fe and rust is FeO, iron oxide. Okay, so you have new substances are formed, so it's a chemical property. Dynamite, the fact that it can't explode is a property, and the fact that you watch it explode means that you're destroying the dynamite. Okay, new substances are formed. Measuring the density of something is how fluffy or how compact it is. Okay, it's mass per volume. That doesn't hurt uranium. Okay, we already talked about when you melt something, melting aluminum at that characteristic temperature of 933 Kelvin. It's a physical property, and again, color is a physical property. So this is one where you may or may not have run into before. We can also look at something, think of something I'm thinking of game, and characterize properties in terms of being intensive and extensive properties. Intensive properties, I usually start there. I usually pull out the word independent for intensive. It's just kind of a little mnemonic thing I remember. Independent. So it's a property of matter that is independent of how much matter you have. Independent of amount. It doesn't matter how much you have. It's supposed to be amount, independent of amount. An example is color. I mean, we could pick the I'm thinking of game and pick a chair, okay, or 50 chairs, and the property of color is the same. Okay, so color is an intensive property, independent of amount. Now, picking the chairs, right? 1 chair versus 50 chairs. If a property of matter is its mass, okay? So actually, if I have 1 chair, it might weigh, I don't know, 10 pounds, okay? Versus 50 chairs, of course, that'd be 50 pounds, okay? 10 pounds and 50 pounds, those are both properties of those 2 sets of chairs, okay? But they are extensive properties. They do depend upon amount. Okay, so color was an example up here. Independent of amount. Okay, so physical and chemical changes kind of go along with physical and chemical properties. You know that a chemical change has occurred if new substances are formed. chemical change has occurred if new substances are formed. Okay, if something undergoes an apparent metamorphosis, a change that looks different to us, but no new substances are formed, that's a physical change. That's kind of like the melting thing. You're like, oh, it looks different, okay, but it really is simply physical, because on the molecular and atomic scale, no new substances are formed. So here are a list of looking at physical and chemical changes. One of the things I think of with this, I tell students, is a physical change, okay, can be undone. Okay, a chemical change cannot be undone. So with that in mind, if you look at accidentally spilling bleach on something, okay, it can be undone if you get one of those Ritz, like, color things and try to put color over it. But you can't undo that. So that's an example of a chemical change. Of course, when you exhale, and if you see your breath on a cold winter day, the reason you see your breath is the water vapor is condensing. So that's a phase change from gas to liquid. When plants do their thing with making chlorophyll, they use carbon dioxide and ultimately convert it to sugars. So new substances are formed, sugars from carbon dioxide. Butter melting, of course, that's a phase change, so that's a physical change. All right. Dun, dun, dun. So this is the first assignment. This will be due Monday. I know that there was one student I gave a copy of the. Does anybody don't have their book yet? They need that copy of. Okay. Still kind of. And I'll pull these up, but these aren't too bad.
Thank you.
You're welcome. Let's see if I can pull them up. I think I can. I guess I can't. I can't remember how I do it, but I'll just, if you have your book handy, but for instance, number 7 is state whether these are physical or chemical properties, and number 8, which are physical or chemical properties. Okay, and number 9 as a question about, is it a mixture or a substance, and if it's a mixture, what kind of mixture is it, homogeneous or heterogeneous? Okay, that sort of questions. Okay?
When it says 119, do you want us to do 119, or is that just an example?
That's just an example. I was looking at the same, like, well, 119 isn't assigned.
Mhm.
So, like, 17 is due. So, yeah, 119 is not due. Yep. Very good. So let's go on to the next part. Pharmacist parts.
Someone was just playing Jingle Bells, really?
Yeah. Someone's happy. It's Friday. Okay. So, on to something that you probably do need to fill in some blanks with your PowerPoint slides. So, the first few slides seem like kind of, well, I don't know. They're still not getting into the nitty-gritty of it. So, we do a lot of measuring in science, and it's important that when we measure something here in North America, that we can relate that same measurement to China or Korea. So we use reference standards. If you've worked, if you worked out in industry, they will use a lot of balances out in the factory setting, and those balances actually need to be calibrated. So they hire somebody to come in and calibrate them according to a standard that is traceable back to some standard that's international. Okay, so there has to be some standard that we can all agree upon. Okay, have you ever thought about, you know how we say there's 12 inches in a foot, right? So a foot is like a basic unit of length in the English system. You're like, whose foot did they go by? You know, yeah. When we measure things, we might measure mass, length, volume, or temperature, for example. Mass is, in general, the amount of matter that is crammed into an object. Okay. Length is the distance between 2 points. Volume is the amount of space that something occupies. And temperature, we might be tempted to say temperature has to do something with energy, like thermal energy, and it does have something to do with thermal energy. But temperature will not, in and of itself, say how much thermal energy an object has. But one thing temperature will do is if you have something hot A and something cool B, and you allow kind of heat energy to go back between the two, it will go from the hot object to the cool object. Okay. So, the reference standard for mass, this goes again back to the scales out there in industry, actually is stored very carefully in Paris, France. Okay, it happens to be a type of metal that does not decay, or they're hoping doesn't decay. I've read recently where it's lost a little bit of mass, so I don't know how that works. But it's like under a dumbbell jar. So that is the 1 kilogram mass that standards come from. Standards come from that. Now length is a little tricky. Length is something that we all have access to. That is a photon traveling through space, more specifically a photon traveling through no space, or a space that a vacuum's been created. It will travel at about 300 million meters per second. Okay, so a fraction of that, then we can use that to get length. That's not an experiment I can do. Okay. Volume is related to length. Okay, so once you have a meter, if you take a meter cubed, okay, yeah. Time is also something I can't do. Of course, there's the element cesium, one form of cesium, mass number 133, has a particular spectral line, okay, that we can actually use the number of periods that occur in 1 second. So, temperature. Of course, some of you guys know when we get moving into science, one of the temperature scales we need to use is the Kelvin temperature scale. And the Kelvin temperature scale is awesome, and it has actually the coldest Kelvin temperature scale, 0 Kelvin, and that's absolute 0. So that is something that, in theory, we could kind of consider. But 1 unit Kelvin is 1/273.15 fifth of a unit between triple point of water, which is 0 Celsius, and 0 Kelvin. So, some of you guys, I'm sure, have run into the concept of a mole. I love moles. I bet you love moles too. So, mole is a big number. A mole is 6.02, 2 times 10 to the 23rd. So that's when we're talking about counting things, little atoms, little molecules. That's kind of what we use for amount. Instead of using dozens, we use moles. All right. So with regard to measuring volume, this is some glassware that we ran into yesterday checking into lab. Notice that they have gradations. Okay, gradations are the little white marks. Okay, but these gradations give you a different amount of accuracy and precision, and actually that's one of the things we're going to hit on, probably wait and hit it on Monday, might hit some of it today. But this is generally less accurate than this. Okay? But do you guys remember that this thing that has the yellow liquid in it, that's called a volumetric flask? That actually has one nice little line up there, calibration line. So that's even more accurate than your graduated cylinder. So as far as measuring things, again, kind of back to the worldwide international scene, we have these international units of measure. For length, it's the meter. For mass, it's the kilogram, not just the gram. For time, it's the seconds. For temperature, it's the Kelvin units. We said amount would be the mole. Electric current, the ampere, and luminosity, the candle. So it is definitely about metric, okay? I can remember being in 5th grade, and our teacher was like, oh, you know, when you get ready for, of the age of pumping your own gas, when you pump it, it will be in liters. It's not. So she meant well. So I know it says that you need to know these prefixes, but you need to know probably just, I think I marked 5 on the next slide that you need to know. And they're coming up. But you might want to have this handy for some of your homework. So the 5 with arrows are the ones that I would commit to memory, and on a test I might throw at you. So as some of you probably already remember, kilo means 1,000 times the base unit. So over here, I like this because there is actually a kind of a written out example of what do we mean by the prefix kilo. So 1 kilogram is equal to 1 times 10 to the 3rd grams. We're going to do a lot with scientific notation. I hope, let me know if you need help with that. But then, aside from that, the other 3 you need to know actually are smaller than the base unit. Centi means 1/100th, milli means 1/1000th, micro means 1/1,000,000th, and nano means 1/1,000,000,000th of the base unit. Okay, so this is a first look at what we call equivalency statements. So I kind of hold out my hands, and they're equal quantities, and between my hands would be an equal sign. So if we kind of pick on the centi prefix, and in terms of the measured quantity meter or length, okay, 1 centimeter is equal to 1/100th of a meter. Okay. We can, as you know in algebra, if we multiply both sides by the same thing, that's legitimate. Both sides at equality sign. And that's what we're going to do. I'm going to multiply both sides by the amount 100. Okay. Now, in doing that, okay, I recognize that over here on the right side, now I have 100 in the numerator and 100 in the denominator. So those things can cancel. So if I rewrite that, okay, it just looks a little bit different than the one up above it. So now I can say 100 centimeters is equal to 1 meter. But they both correctly equate centimeters and meters. I don't know if that works for you. Okay. So another arrow. There's another arrow for the length relationship between the English and the metric system that you're going to want to memorize. So I won't give you this one. The 1 inch is equal to 2.54 centimeters. The word exactly there is an important one. And that actually will come up, be more apparent what's so special about this exact equality coming up later in this part. And I guess it's exactly, we would call that by definition. That's just the way they set it up. So you don't have to memorize the volume relationship between English and metric, nor do you need to memorize the mass relationship between pound, English and metric. But you might need to use them, but you don't need to memorize them. All right. So within the English system, within the metric system, there is one more important equality that you need to memorize. You may already know this. 1 milliliter is exactly equal to 1 cubic centimeter. So, cute. Okay. See, again, the stuff you probably already know. Okay, so case, like uppercase, lowercase, does matter. So grams is a lowercase g, meters a lowercase m, liters in uppercase L, seconds, lowercase s, cubic meters, meters raised to the third power. Okay. So case does matter. Okay, uppercase, lowercase. Don't put it's so tempting to put a little period at the end. No, grams is not GM period, it's GM. Wait, it's not even GM, drat. It's G for grams. Don't without the period. The other thing is we never put tack an S on the end. Okay. So on to accuracy versus precision, and it really lends itself. Anybody in here play darts? Maybe watch or play darts, okay. And in darts, you want to get into the center, right? So that's your goal, okay. And I think this concept of accuracy and precision really lends itself to kind of a dartboard and thinking of how close you can get to the center. So accuracy is you know your target and how well you can get to your target. That's accuracy. Precision is how much you can hit the same place. Okay, so precision is scatter. Okay, accuracy is are you on the true value? Okay, so here we go. The bullseye is the goal. Okay, so here it looks like quite a bit of scatter, relatively poor precision, and the scatter isn't centered around the bullseye. Okay, if it was kind of centered around the bullseye, you could kind of average those together, and you could maybe say pretty good accuracy, but bad accuracy too. Here, a really tight cluster, so the precision is there, okay, but the accuracy is not. I mentioned, like, if you send away a sample, like a soil sample for analysis, when they send it back to you, they have to tell you how their performance is with regard to that analysis. They will give you the statistics on their precision and accuracy for that analysis. And there we go. The last scenario I've got up here is it's tightly clustered, so the precision is great, and it's clustered on where it's supposed to be, so, okay. And I guess I would argue, though, kind of like I alluded to a minute ago, there's one more scenario where you have, here's the bullseye, okay, and to me, I think it's possible that you have a situation where, oops, do that. They aren't very tight, so the precision sucks, okay, but if you average them all together, they're pretty accurate, okay. Okay. So, how far off you are from the correct value, now we're kind of switching from darts to probably more measured quantities. A lot of times we know what the real value is. How far you are off from the real value is error. There's different ways of expressing error. Okay. How unreproducible your analysis is, okay, is associated with precision, and we generally call that uncertainty, okay? So there's error and uncertainty. So error is how far off you are from the true value, and uncertainty is what sort of spread you have in, if you do this measurement again, It's amazing when push comes to shove and you go to do an analysis, for real analysis, it is amazing where you think you get the same number, or you think and it doesn't. So that sort of play is uncertainty. So different ways of expressing how far off you are. Okay, so absolute error is you take the difference between your known value, sometimes we call that your theoretical value, versus what you got. It's like a subtraction problem. Absolute error, absolute uncertainty. So sometimes when you do an experiment, you'll know the value and you'll go like, okay, so how far off am I? By difference, absolute error. There's this other called relative error or relative uncertainty, and you do one more step beyond absolute error. What you do is you take the difference and you divide it by the theoretical, or the difference divided by the known value. Okay? So that's the absolute error divided by the known value. Times 100% if you're going for percent. Okay. So I think I'm going to take a running start at this on Monday, because I don't want to leave you hanging with significant figures. Okay? So that's where I want to stop. If you have any questions, let me know. Otherwise, you're free to go. Didn't we get out early last time, too? Might be a pattern, I don't know.